Hello, y'all. Welcome to lesson 66, reactivity 1.1.2 and 3. We're going to be talking about how reactions are described as endo or exothermic, depending on the direction of energy transfer between the system and surroundings. We're going to understand temperature change, decrease or increase that accompanies endothermic and exothermic reactions. And we're going to talk about relative stability of reactants and products, which determines whether reactions are endothermic and exothermic, and we'll sketch and interpret energy profiles for these two reactions. So, with this said, let's go right into it. We discussed how reactions either absorb or release energy, and this is what this whole unit's going to be about, And this is basically what we do when we classify the direction of energy transfer. When we talk about absorbing and releasing, that means from what to what. So generally what we do is we look at systems and surroundings. So we already discussed systems and surrounding in a previous unit or previous video, but if we have something like a match and we light that match on fire, we would generally classify the match itself as the system and the outside air as the surroundings. So this would be a release of energy as energy moves from the system into the surroundings. That would be a release, and we see that in the form of heat and light. However, opposite, we could have a ice cube. And ice cubes tend to melt, and so we'll have a little puddle here. And so as that ice cube melts, it's getting that energy to melt from somewhere, and that would be the surroundings. Energy from the surroundings are moving into our system. And so that would be an absorption of energy. So this direction of energy transfer is how we classify reactions. So when we have energy leaving, we call this exothermic. Exothermic specifically means a release of energy from the system to the surroundings. Otherwise, the other reaction is endothermic. This would be the absorption of energy from the surroundings to the system. So those are two types of reactions. Generally, when we think of a release of energy, temperature will increase. When you use a match, it gets hot around the flame. And when we absorb energy, temperature usually decreases. For example, if you have that ice cube in your hand, it's going to get cold as it melts. We definitely have some physical ways of looking at this, and these would be changes of state. So if we have our solid state, our liquid state, and our gaseous state, as we go from solid to gas, that requires absorbing energy. So that would be endothermic. As we go from gas to solid, it's losing energy. That would be exothermic. So for example, our ice cube is going from solid to liquid. That is an endothermic change. These are always true with these states of matter. Always true. Now, when we do this, we know our actual reactions also have some that are always exo or always endo. just as these changes of state are. So for exothermic reactions, a couple reactions that are always exothermic. One is combustion, which is burning. It can be combustion of a hydrocarbon or combustion of a metal. Generally, when we have some hydrocarbon CXHYOZ and we react with oxygen and we get H2O plus CO2, that is our combustion reaction. It is always exothermic. Furthermore, neutralization between an acid and a base is also always going to be exothermic. That generally looks like HA plus BOH, A referring to our acid, BOH referring to our base. This will always create Ba as our salt plus H2O. This is always going to be exothermic. All right. Now we also have our endothermic reactions that will always be endothermic. These examples are photosynthesis. This is a light-dependent reaction. It takes energy from the sun. This is light waves, so this would be radiation, the way the energy is moving from the sun to the plant. And this reaction you should just have memorized, honestly. We take 6 carbon dioxides plus 6 waters, and we convert that into C6H12O6 plus 6 oxygen. This is the standard reaction for photosynthesis, and we'll even put our state symbols in here. This is a reaction that the IB expects you to know already. The other one is thermal decomposition. That's the application of heat to break something up. One good example of this might be the thermal decomposition of a carbonate like calcium carbonate, CaCO3. When you add heat to calcium carbonate, you get calcium oxide, calcium oxide plus carbon dioxide. This will be in solid form and this will be in the gaseous form. So these reactions always have either endo or exothermic profiles. So what happens to temperature during this? We already said there's a general statement, but why does it happen? So when temp is measured, the key is we're measuring surroundings. When you think about putting your thermometer in a solution, the thermometer itself is a surrounding, even if it's in a chemical reaction that's happening. If we look at, for example, the combination of NaOH and HCl, so hydrochloric acid and sodium hydroxide, and we put a little thermometer in there, and we zoom into the particles. Our actual reaction is HCl plus NaOH reacts to form H2O plus NaCl. And this is going to release energy. It releases it right into the water molecules that are surrounding this. As it releases that energy, the water is going to increase in temperature, causing an increase on our thermometer. Specifically, the water or the solvent in these reactions, solvent, and as the solvent, it is therefore the surroundings. This will lead to an increase in Ke, kinetic energy of the water. And if we remember, temperature is just a measure of the average kinetic energy. So this is kind of that flow chart of the energy comes from the reaction into the water, causing these particles to move around way faster. They move around faster with a larger KE. They'll interact with the thermometer, hitting the particles in there, causing that to increase. And the temperature overall will be measured as an increase. So that's kind of what happens in an exothermic reaction. But what about an endothermic reaction? Endothermic is something that we actually have a bit of experience thinking of all the time. Generally think of evaporation. If you have your arm, and we're going to witness my terrible drawing skills, and on top of your arm, you've got some water. That water starts feeling cold on your body. Maybe if you step out of the shower, bath, or swimming pool or whatever. But what's actually happening is energy is being drawn from your arm into the water, and little water particles will evaporate off once they get enough energy from your body. So really, you're feeling the lack of energy. The energy absorbed by water is felt as coldness. And that's our endothermic reaction. That's why they feel cold. Generally, when you're feeling cold, it's not because the surroundings themselves are interacting with you, making you cold. They're not giving you cold, but what they're doing is taking away heat. So something you should be thinking about is that coldness is really just the loss of heat. Something that people used to say, or people still say, is when you open a door in an air-conditioned room or your refrigerator, they say you're letting the cold out. But really what you're doing is letting the heat in. So this is a little bit of our endo and exothermic reactions. What we now need to look at are energy profiles. So what the heck are energy profiles and how do we use them? Well, energy profiles are what we use when we're looking at products and reactants, and we're comparing relative energies. So like which one has more, which one has less energy. Because the energy in these, so the energy is based in the arrangement of atoms and bonds. Different bonds have different energies, and if you have more atoms to bond with, more double bonds, triple bonds, or bonds even between different atoms, you're going to have different amounts of energies. So we use an energy profile to represent the energy difference between reactants and products. So what do these profiles actually look like? Well, this is what the IB wants you to be able to draw and read. So we'll do two different energy profiles. And I'll put my units here, energy, and this is specifically chemical potential energy because it's the energy in bonds. And on our x-axis, we'll have reaction coordinate. That's just kind of a fancy way of saying, are we in the reactants or the products? And so I'm just going to duplicate this real quick. So over here, we'll do exothermic. And over here, we'll have endothermic. And so in an exothermic, our reactants are going to start pretty high, while in endothermic, our reactants will start pretty low. And in exothermic, our reactants lose that energy. So our products are going to have lower energy than our reactants. And endothermic, our products are going to have higher energy than our reactants. So as we draw this, we're going to have reactants, products, and this is going to be our energy released. Meanwhile, over here, we'll have reactants, products, and this is our energy gained. So this is what a reaction profile looks like. It's just a graph showing the difference in energy between the reactants and the products. The final aspect here is just a notice about stability. The lower the chemical potential energy of a coordinate is, so like our reactant or our product, that equals to a greater stability. You can think about it like electrons in energy levels. They want to be in the lowest possible energy level. Well, reactants and products tend to want to be in the lowest chemical potential energy. Therefore, they are more stable. So exothermic reactions tend to create more stable products than endothermic reactions. Anyways, I hope this helps you understand endo and exothermic a little bit better, and have a great day.